Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is lecture series on analog signal processing, and we are discussing the topic design of GICs, that is general impedance converters, where we have convert L circuits to the generally impedance. In the last lecture, we have discussed that the implementation of these GICs in the ladder circuits. We have discussed that what are the ladder circuits, which are the repetitive LC circuits with the no R components, and we have doubly ended LC lossless ladders where R components are in input and the output. Then we have discussed the realization of these simple ladders with active components. We have discussed there are three different types by which we can have the active realization of these components. The first one is the realization using element replacement. In element replacement, we have to use GI circuits in place of L. So, but we have discussed that there is a more number of op-amps are required to design a floating inductor. For example, if we use GICs, then we need, for one inductor, we need 4 op-amps for the inductor circuit. So it makes it bulkier as well as the costlier. There are another techniques which are the Gauss Key Profile technique and the Bruton's technique to simulate the behavior of the inductor as an active device. So in the Gauss Key Profile technique we will discuss today, and Bruton's technique we will discuss today. In Gauss Key Profile technique we have a GIC circuit. Let's suppose we have GIC circuit that we have discussed in the previous lectures. In GIC2 circuit, if we can take it as Z11, which is the input impedance, that can be taken as STR5. You can see the lecture number 3 of unit 4 for this derivation. Here we have designed this input impedance Z11 by the equation as the load resistance, which is converted into an inductor by multiplying a resistor by its time constant T. R5 is the fifth resistance of GIC2 circuit, which is when T is the time constant given by 1 by RC. So if we have in GIC2 circuit, if we have R2 is equal to R3, then to obtain an lossless inductor, we can have V1 by I1 is equal to SC4 R1 V2 by I1. And we have seen that RC can be taken as T. So we can say that input impedance, that is V1 by I1, is equal to ST into V2 by I2. So if we assume that the ideal op-amp input and output ports are related of the GIC, then we can say that V1 is equal to V2, and so if we take these from this equation, if V1 is equal to V2, then we can say that I2 is equal to STI1. Or we can say that the ratio of I1 and I2 is ST ratio 1. So adopting a simplifying representation of GIC can be TS ratio 1, which is the relationship between the input and the output currents. Input current is ST and output current is voltage is 1. So if we have the whole circuit, GIC circuit, that can be represented by ST ratio 1. This can represent a relationship between the input and the output currents to the ratio of the voltages, and R5 can be taken over this load resistance over here. So the whole GIC circuit can be represented in this way as the ratio of the currents to the ratio of the voltages. So in this figure, if we say that the principal approach for the simulating inductor behavior in the ladder. This first figure, it contains a resistive circuit with one resistor R, and we can connect a GIC into input branch. If we label the input current and the voltages of the resistive circuit as IR and the VIR, the voltages and the current in the input of the GIC circuit can be given by VIR is equal to V1, the input current is equal to the output current or voltage, and the input resistance is equal to V2, I2, that is output current is equal to ST into I1, as we have seen in the previous slide also. So here we can see that IR is equal to VIR. Simple this. And we have seen V1 by I1 is equal to SL, where L is STR, T is the time constant. So this whole circuit can behave as an inductor with L is equal to TR. T is the time constant and R is the resistor. So this whole circuit can be represented, converted by resistor and the inductor to simulate the behavior of the inductor by TR. Now, if we see that inserting a GIC into the input branch of single resistor network makes the resistor R in the combined network look like an inductor, which is L is equal to TR. Now again, if we see that this is one V1 and other part is grounded. Now for floating inductor, which was realized from a resistor with the help of the two GIC, is a special case of this transformation. So now if we have, let's suppose, a circuit with these different inductors, a circuit with 4 different L's, different inductors, then we can replace this circuit with the equivalent resistor network, and we can have a GIC for that one. So the representation of this circuit inductor can be given by the resistance in place of the inductors, and wherever we have replaced resistance, we need to have GIC. So GIC is replaced with a block of ST ratio 1. So this inductor is replaced by ST ratio 1. This inductor is also replaced by ST ratio 1 with the resistor R1. This inductor is also replaced with ST ratio 1. So this process is not limited to a single resistor or even to the two-port network. So if we have, let's suppose, more than one port for this network, let's suppose there are 3 ports, 1, 2, 3, then we can have different voltage equation for these 3 ports, which are represented by these 1, 2, 3 equations. In the vector form, we can represent as voltages is equal to resistance and into currents in that branch. And the resistances, if we see, it can be taken as R1 plus R4 for VIR. And similarly for all the resistances we can represent here. In the vector form, I can represent it as VR is equal to R into IR, where IR is the vector form of I1R, I2R, I3R, and R is the matrix of the resistance. After embedding this network to the GIC, we can have the different forms of the V1 and V2 and V3. So these V1 to V3 forms can be written by using this equation, by implementing the GIC. So these three equations that are used by GIC can be given by the three vectors, which is V is equal to I, ST, IQ. Now if we say this is from this equation, it is STR into I. And previously we have said that it is V is equal to IR. So here we can say that R is equal to STR, or we can say that STR is an inductive impedance, or we can say that this R is SL. So in the previous this matrix, I can replace this resistance with the inductor. So wherever R, I can represent R as L1 plus L4 plus L4 L4 and so on. So I have all L's can be represented by this V. That means in this circuit, wherever there is the resistance, that is simulating the behavior of inductor. So we can have inductive behavior of the resistance. Similarly, we can conclude that for the active simulation of the given ladder circuit, the following rules has to be followed. First one is that all an inductor sub networks which are separated from the different networks by using cut. Let's suppose for this network, if we have a ladder circuit, if we have a cut from this circuit by inductors, then each cut is to be replaced by GIC circuit in such a way that its output is phased inductor subnetwork. Then lastly, the sub-inductive subnetwork is replaced by resistance as in the previous case. That resistance will be equal to LIT. Ith resistance will be equal to ith inductive by time constant. So the third step in the steps, wherever I have cuts, I will replace it with the resistance and the GIC. So I have replaced inductor with resistance of L by T, and the cut is replaced by ST ratio 1, which is GIC. So in this way, this whole circuit is represented in the form of GICs. So in this way, if we have any circuit, any ladder circuit, we can replace the inductors by GIC. This technique is known as the Gauss Key Profile technique. Another technique is Bruton's FDNR technique. Now FDNR is a frequency dependent negative resistance. For this technique, first of all, we know that the resistance, general equations of resistance, inductor and capacitor is given here. The resistance can be taken as R, L can be taken as SL, and C can be taken as 1 by SC. Now, if we normalize all these components by S, if we divide it by S, then R will be 1 by R by S, S will be cancelled out, so it will be L only, and C will be 1 by S square C. Now see, if we see here, this resistor which was equal to R, this resistive circuit will be acting as some capacitive circuit, 1 by R, 1 by S. That means this is behaving as capacitor. This inductor will be behaving as L. So this will be behaving as a resistive circuit because there is no S term present in this one. And lastly, there is a new term which is 1 by S square, which is not a general for the R, L or C circle. So for normalized values, we find that resistor became capacitor with the value of with the value of 1 by R, and L becomes resistive with value of L, and C has a new term which is 1 by S square C. Let's suppose that is D. Now let's focus on this D. This D is known as the FDNR, frequency dependent negative resistance, because there is S term involved in it. So I can write it as in terms of J omega as, if I put S is equal to J omega, it will be minus of 1 upon omega square C. So it is negative dependent upon omega. So this ZC is frequency dependent, omega dependent, negative value of resistance. That's why it is called FDNR. Another thing, if we say it is a frequency dependent, and for second thing is it is a negative. So also it is called the supercapacitor. It is also called supercapacitor, but mostly it is known as FDNR. And its representation is double capacitor or 4 parallel lines. Now if we design FDNR, how we can design FDNR? Simple GIC circuit. We have simple GIC circuit with equation this one. All the 5 impedances given by odd impedances divided by even impedances, that is Z3 into Z3, Z1 into Z3 into Z5 divided by Z2 by Z4 will be the input impedance, or in terms of conductances I will have Y2 into Y4 divided by Y1, Y3, Y5. Now if we have any two conductances over here as capacitor, any two capacitor, let's suppose 1 and 5, 3 we do not take as we have discussed in the previous lecture. So let's suppose we have 1 and 5 as a capacitor. Now if we replace this one as capacitor, it will be S into C1 and C5, G2, Y2, Y4 and Y5 are the resistive, so we can take it as G4, G5, G3 and G2. Now if we see here, there is S square term, and the whole term the rest of the term we can take it as 1 by D. So this is, so we can take it as an FDNR. So this circuit with Y1 and Y5 as capacitive loads, capacitive components will act as an FDNR. So here D can be defined as C2 into R4 when R3 is equal to R2. So if it will have a unit of amplitude A square S square by V, or Faraday seconds. Similar to the earlier GIC circuits, we can show that we can have R2 is equal to R4. So we have FDNR circuit that can be represented as at the first and the fifth place as capacitive, and R2, R3, R4 as the resistance in GIC. So in this way we can have FDNR placed in this Bruton's technique. So thank you. In this lecture we have discussed the replacement of the inductor by the two techniques. One is known as the Gauss Key Profile technique, and other technique is known as the Bruton's FDNR technique. We have discussed another important component which is frequency dependent negative resistance. We have seen that when we have normalized the components, then we can replace the conductor, inductor and the capacitor, inductor and the resistance by the new components, which is the FDNR, also known as the superconductor. So by this way we are completing this unit. Thank you.